Optimization problems are simply applications of the max-min problems we've already been working. The only difference is that we're not always given the equations needed. So you may have to read the problem carefully and then figure out what the equation is that we're actually trying to maximize or minimize. So let's look at some examples. Alright, example number 1. Find two non-negative numbers whose sum is 20 and whose product is as large as possible. So this is an optimization problem that happens to be a maximum. We want to maximize this problem because of the words as large as possible. Alright, so you want to look for those clues because they're not going to always come right out and say find a max, find a min. Maybe as large as possible, maybe the smallest, the least, the greatest. So you're going to look for those keywords. Okay, so two non-negative numbers whose sum is 20 and whose product is as large as possible. So we have no equation given to us, but we have enough information to then write an equation that we can work with. So what is it that we want to maximize or minimize? We want to maximize or minimize the product. And I'm going to just let P represent product. And I need it to equal two numbers that are being multiplied together. I don't have any variables, but I can define my own variables. So I'm just going to let X stand for one of the numbers and Y stand for the other number. It's possible that they're the same numbers. It's possible that they're different numbers. All we know is that they need to be non-negative. So we're just right now going to let X and Y stand for those two numbers. We also know that the X plus Y has to equal 20. So that's all the information we've been given. Okay, so we have two equations. Now it's important for us to understand which equation is our main equation. The equation that is the one that's being maximized or minimized is what we call our primary equation. And so this first one that I wrote is the primary equation. So this is the one we're actually going to take the derivative of. Okay. The X plus Y equals 20 is what we call a secondary equation. And the purpose of the secondary equation is really just to help us rewrite the first equation, the primary equation, in terms of only one variable. Because see how we have X and Y in our product in our primary equation? I would prefer to have either only X or only Y so that I'm not having to deal with both of those when I take the derivative. So I'm going to use my secondary equation to write the primary equation in terms of either just X or just Y. And you choose. It doesn't matter in most cases which letter, which variable you decide to get rid of. So I'm going to keep my X just because I feel like it, which means that I'm going to rewrite my secondary equation. I'm going to solve it for Y. So Y equals 20 minus X. You could do this by solving for X and getting 20 minus Y. It's not going to matter. And then I'm going to plug that into my primary equation. So I now have P equals X times, and instead of Y, I'm going to write 20 minus X because that's what Y equals. Okay? And I'm going to go ahead and just distribute. So that equals 20x minus x squared. So now I have an equation. Whoa, that's a really big squared there. Let me see if I can fix that. I'm not sure. Do it this way. Okay, so that just looked a little silly. Okay, there we go. So now we've got our product equals 20x minus x squared. Now we're ready to maximize this. As we've been working problems in the past, we know that maximizing involves taking the derivative. So we're going to take the derivative p prime equals 20 minus 2x. And then we set this equal to 0. We find the critical numbers. We set it equal to 0 and solve. So 20 minus 2x. So when you work that out, you're going to get x equals 10. Okay, you need to stop for a minute and think, ask yourself whether or not this makes sense, and look back at the original problem. We want two non-negative numbers, so that means that our domain, the lowest it can be is 0. It could actually be 0 because that's non-negative, instead of if it had just said positive. That might not include 0 then, but we could include 0. And the largest it could be is 20 because we need the sum of the two to equal 20. And since it can't be negative, then the second one could not be larger than 20, or else you'd have a sum that was greater than 20. So 10 is in our domain. It is between 0 and 20, so that is a reasonable answer. So now all we need to do is solve for y. And we're going to plug this back in. Which equation do we want to plug it into? Well, if I were to plug it into my primary equation, I wouldn't be able to solve for y because I don't have any numbers or anything else in there to help me. Once I plug 10 in for x, I'd still have a p and a y. That wouldn't tell me what it was. So I'm not going to plug it into the primary. I'm going to actually plug it into the secondary. And so this is another function that we use our secondary equation for. You won't always have a secondary equation, but in this particular case, and many times we do. And so in this case, we'll use it to help us then solve for the second variable. So 10 plus y equals 20. And so in this case, y is also 10, which is also in our domain. So therefore, our solution is x equals 10 and y equals 10. And I would expect you to write a nice little, not paragraph, a nice little sentence just summarizing that up. But those are the two numbers, two non-negative numbers whose sum is 20 and whose product is as large as possible. Example number 2. A 216 meter squared rectangular pea patch is to be enclosed by a fence and divided into two equal parts by another fence parallel to one of the sides. What dimensions for the outer rectangle will require the smallest total length of fence, and how much fence will be needed? So sometimes you're going to have to just draw a picture before you get started to understand what's going on. Okay, so we have a pea patch. I hate peas, but I guess some people like them, and so farmers want to grow them. So here's our pea patch. And the area of this pea patch is 216 meters squared. Okay, and it says that it's divided into two equal parts by another fence parallel to one of the sides. So it doesn't matter whether I draw this dividing line vertically or horizontally. I'm just going to cut it in half. We're going to pretend that those are equal lengths, and that's what this picture looks like. Okay, so we want to find the smallest total length of fence. So this is a minimum problem. We want to minimize the perimeter of this fence. Okay, so the first thing we need to do is come up with, now that we have a picture and understand what's going on, we want to come up with variables. Again, it doesn't matter. You could use L and W for length and width. You could use, X and Y, just anything. So I'm going to stick with X and Y's because that's what we tend to be comfortable with. But again, you do not have to stay with those variables. I'm going to let X be this vertical length here. And so what I have is I have an X there, I have an X length of fence there, and I have an X length of fence there. And then I'm going to have Y be the horizontal piece, and I'm actually going to do the horizontal piece for each little rectangle since we have that little dividing line in there. Okay, so the perimeter of this fence, which is what I want to minimize, is going to be 3 X's plus 4 Y's. Now that's the perimeter of the whole thing. The problem is asking for the dimensions of the outer rectangle, And so we'll find those dimensions. But in order for us to find what x and what y is, then we're going to need to take into account all of the fence. In the second question, especially how much fence will be needed, will include that dividing line, that middle, the middle fence right here. And so that's why we're using 3 x's and 4 y's, even though we're going to minimize that the outer rectangle. So since this is what is going to be minimized, this is our primary equation, we need our secondary equation, and our secondary equation is going to use the area. So 216 equals x, which is our height, if you will, or our width, times 2y, because that length, or the base, is 2y's. Okay, so I can rewrite that 216 equals 2xy, and just to make my life easier, I'm going to divide through by the 2, and so xy equals 108. And then just like we did on the last problem, we're going to solve for either x or y, and then substitute in to our primary equation so that we can get that in terms of just one variable. So I'm going to leave x over here and divide by y, and so I'll get 108 divided by y. So I'm going to substitute that in up here. So I have perimeter equals 3, and in this case x is 108 over y. This problem, I decided to keep my y's in there. Okay, so now just to clean it up a little bit, so this is going to be 324 over y plus 4y. All right, and this is what we're going to minimize, so we're going to take its derivative. Okay, so we could rewrite that. That would be 324. I'm just going to write it over here. 324 divided by y is the same thing as 324 y to the negative 1. Okay, so when we're taking the derivative, it might be easier for you to, that's messy, sorry, to do that as a power rule. But either way, we're going to end up with 324, negative 324 over y squared plus 4. Okay. And when I do this and I get something that looks like this, then I prefer to go ahead and get a common denominator and have it just as one fraction. You can work it, in multiple different ways. So, but just know that's what I'm choosing to do. So this will be negative 324 plus 4y squared, all of that over y squared, and that equals p prime. Okay, so now we're ready to minimize. So we make this b equal to 0. We only need to worry about the numerator in that case, because this whole fraction will only be 0 when the numerator is 0. So negative 324 plus 4y squared. So 4y squared will equal 324. And if I divide, then y squared will equal 81. And y will equal technically plus or minus 9. But since this is a length, then negative numbers would not be in our domain. If we go back up there and talk about domain, we got to be talking about the context. The context has to be positive here since it's lengths. So we're only going to deal with, so y is going to equal positive 9. Okay, so now we know that this is 9 and this is 9. So that whole length then would be 18. And we need to solve for x. Erase this over here. All right, so if 216 equals x times 2y, that was our area formula. our secondary equation, we're going to plug in. And it is okay, as long as you're careful with your arithmetic, to use the simplified one. Okay, so 108 equals x times 9. And so when we divide, then x is going to equal 12. So what we've got is that our dimensions of our outer fence, because that's what the problem asked for, the dimensions would be 12 meters by 18 meters. And that would answer the first question. And yes, I'm out of room, so I can't do it, but I do expect you to write a sentence. The dimensions for the outer rectangle with the smallest total length of fence would be 12 meters by 18 meters. And then how much total fence would be needed, that's when we'll come back and use our primary equation and plug all those numbers in. So what we've got is the perimeter will equal 3 times 12 plus 4 times 9. Ooh, I'm out of room, sorry. And that's going to be 36 plus 36. So that would be 72 meters total. And that's the total amount of fence, including that inner divider line. Okay, so these are the types of problems you're going to work on in class tomorrow. So just look over these and see, make sure you understand what's going on in these two. If you have questions, write them down, make yourself a note so you can ask some questions. You're welcome to email me or put it on the discussion board tonight. Otherwise, you can ask me tomorrow. Have a good evening.